Yeah, thank you, Thomas, for the introduction. And I thank both organizers for inviting me and giving me the opportunity to present my most recent research project here in front of this audience. In my talk, I will also speak about 1 and 2 particle correlation functions, but in some sense, I will speak more about problems which appear when we are calculating them, and in particular about problems which appear when we are calculating them not exactly but perturbatively. So let me start with a short introduction, and I will rush through this first slide since you have already seen it in the previous talk. So a good way to describe a correlated many-body system is to look at n-particle excitations, and these are described by so-called Green's functions. So this is, of course, more convenient in many perspectives than using this many-body wave function for an Avogadro number of particles. And we have already learned that the most important ones are the one-particle Green's function, so which includes the self-energy, which describes the one-particle scattering of an excitation when it propagates through the solid, and on the other hand, the two-particle vertex function, which describes the scattering events of two excited particles. And both of these correlation functions, as we have already learned, correspond also to certain experiments. So you can indeed measure these quantities. So in order to calculate such correlation functions, we need a model, and the Hubbard model is arguably the most simple model for correlated systems, where correlation effects enter via a purely local Hubbard interaction between two electrons at the same lattice side. However, in spite of its simplicity, this model cannot be solved exactly, and in this respect, the dynamical mean field theory has presented a huge step forward, which maps actually the system of electrons on an interacting lattice onto a single interacting side embedded into a self-consistent path. So this corresponds to an effective Anderson impurity model. And in this way, local correlations are described exactly by a local but frequency-dependent self-energy, which is obtained from this auxiliary Anderson impurity model, while non-local correlations remain on a mean field level. The question is, when are such non-local correlations important? And that is the case for low-dimensional systems, or more general for systems with a low coordination number, because then the average over the neighboring sides is not very good anymore, or on the other side, at low temperatures, close to second-order phase transition, where you find strong non-local fluctuations. So what can we do in this situation? And I want to give you kind of an overview which kind of methods work well in which kind of this generic interaction versus temperature phase diagram. And I want to discuss this in terms of Feynman diagrams. So let me start at small interaction and high values of the temperature. In this case, usually finite order perturbation theory already gives a good result, while when we go to strong interaction, we have already heard or seen on the previous slide that the dynamical mean field theory captures these strong local fluctuations. In the opposite limit of small interaction and low temperatures, we are typically concerned with strong non-local long range, for instance, antiferromagnetic spin fluctuations. And it's well known that they are captured by so-called ladder diagrams built from the Baire interaction and the Baire-Green's function G0. In the most challenging situation of strong coupling and low temperatures, we are concerned with both local and non-local fluctuations of equal size, and to describe them, we have to use the best of both worlds, so to say. So we have to use ladder diagrams to describe the non-local part of the correlations, but we do not start from a bare interaction, but we replace this bare interaction by the frequency-dependent vertex of DMFT, which already includes all local correlation effects right from the beginning. So these methods are called diagrammatic extensions of DMFT. So you start from DMFT and build diagrams from a DMFT starting point, and this is very nice. However, now let me come to the problems of such theories. And to this end, I will give you a kind of an overview about consistency relations between different correlation functions, and in particular between correlation functions at the one and the two particle level. And I will also try to make this a bit more physical, to relate all of them to physical principles. So let me start with the first one, the Pauli principle, which also implies certain crossing symmetries in correlation functions. So that means if you have two fermions, and on the paper, if you exchange them, you get a minus, or in other words, there cannot be two fermions in the same quantum state. And from this, you obtain a relation where on the left-hand side, you have a two-particle quantity. So this is an up-up susceptibility, so a sum of charge and spin susceptibility. And if you sum the susceptibilities, this is a two-particle quantity over frequency and momentum, you obtain a one-particle quantity, and in this case, a very simple one, that's just the density of particles in the system. A second very fundamental consistency relation is comes from the microscopic dynamics, and this you have already seen in the previous talk of Alessandro. It's the equation of motion which relates the self-energy to the vertex function. So here is the diagrammatic representation, and it originates from just taking a time derivative of the one particle Green's function. Also, this can be related to a more to a physical observable, namely to the potential energy, which you can calculate from two-particle level from now the up-down susceptibility, so from a difference between charge and spin susceptibility, but you can also obtain it from the one particle self-energy and Green's function by this Galinsky-Migdal formula. And finally, let me come to the third large group of consistency relations which originate from conservation laws. I will focus here on particle number conservation. So let's look at this lattice side I here, and how the density or the number of particle changes. This is of course due to electrons hopping away from this lattice side and electrons hopping to this lattice side, and also this relation can be rewritten after quite a lot of algebra to something which is a bit more, probably more physical. You can show that the kinetic energy, which is typically a one particle quantity involving just the Green's function, can be also expressed in a two particle way by these susceptibilities. So these are all exact relations, and if we would live in a perfect world and we do calculations with our methods, we would like, of course, that these relations are fulfilled. The question is, are they? And to get a bit of an understanding, I want to discuss now two different types of approximations which fulfill either one or the other of these relations. So let me start with the Pauli principle and the equation of motion. So these were the first two consistency relations. And in this respect, I will now speak about the so-called Paquet formalism, which is supplemented by beta-cell-beta equation, and very importantly by the equation of motion. So this formalism is very complicated. It considers the mutual screening effects between the vertex functions in different scattering channels. I do not want to go into more detail now. The important thing is that you have only one input quantity to calculate everything. So all 1 and 2 particle correlation function, that is the fully irreducible vertex lambda, which you have to approximate in practice, and you can approximate it either by setting it to the bare interaction, or if you want to use a diagrammatic extension of DMFT, you can replace it by a local vertex of the Anderson impurity model of DMFT, and this corresponds to the parquet D gamma A. This type of theory respects the Pauli principle and the equation of motion by construction. However, it violates conservation laws and word identities. And I have shown you this conservation law, which makes some consistency relation for the kinetic energy. But this is another way in which you can rewrite the conservation law from the previous slide. You can look at the left-hand side, which is kind of a delta sigma. The right-hand side is kind of a delta G. And in the recent paper of Patrick Chalupa, Fabian Kugler, who is here in the audience, and I think also Jan van Delft and Alessandro were involved, if I'm not mistaken. They have actually calculated the difference from the right and left-hand side of this conservation law, and you can see that the Paquet approximation, which is this black result here, shows a clear deviation from 0, so they should be the same, so this difference should be 0, and this even increase with u. So one could think now, okay, could I basically make a better choice for this irreducible vertex lambda? So this is my only approximation to fulfill this conservation law, and actually it was already shown at the beginning of the 90s that this is not possible, that each choice of lambda, which is only approximate, will result in a violation of such conservation laws. So that means only the exact lambda will restore it, which would correspond to the exact solution of the problem. The second type of approximations respect the conservation laws. They are called conserving approximations. As was shown already by Beim and Kadanov in the 60s, these can be obtained by constructing diagrams from a so-called Lattinger-Ward functional. So here you have functional, and the first derivative is the self-energy. The second one is the vertex function. And if you construct your correlation functions in this way, then they are conserving. So typical conserving approximations are Hartree and random phase approximation. The Hartree approximation has this very simple Lattinger-Ward functional. If you differentiate, which means cutting a line, you get the self-energy, which is just the Hartree self-energy. And if you cut two lines, the irreducible vertex is just the bare interaction U. Another example is a dynamical mean field theory, where you just have as a Lattinger functional, the Lattinger functional of all local Green's functions. In this way, however, the Pauli principle and the equation of motions are typically violated, while conservation laws and word identities, as I already announced, are fulfilled. This is just a side remark. In DMFT, DMFT has actually this Lattinger functional. Nevertheless, it's not fully conserving because it's a local theory. It violates momentum conservation. So what happens now? Can we now see this also in practice, this violation of Pauli principle and or equation of motion? And there was a very nice work of Eric van Loon, who is also here in the audience, who demonstrated that when you calculate the potential energy from the two-particle level, so this is this DMFT X curve. So here you can see it's actually not potential energy, it's double occupancy, but this is just a factor of u different from the potential energy. So you can see here in this, I think it's blue, yeah, and this blue line, this is from the two-particle level, while the red curve is the potential energy from the one-particle level. And again, with increasing u, this difference even increases. So what can we do about this? So we know now it's very difficult actually to find a diagrammatic approximation which fulfill both consistency relation if it's not exact. And now I want to present you a new approach which I introduced with my PhD students. So we started actually from these consistency relations for the susceptibilities, and on the right-hand side, self-energy and Green's function. And the main idea is to perform a renormalization of these physical susceptibilities, as was already introduced by Toro Moria. So what you do is you take the inverse here of your physical susceptibility, you add a so-called lambda correction parameter lambda to obtain a lambda corrected susceptibility. And if we consider now a exact lambda, we could of course get, if we find somehow the exact value of lambda of omega and q, we can find an exact susceptibility. So our approximation now is that we consider a constant lambda, which has a very transparent physical meaning if we consider an Ornstein-Zernike form of our susceptibility. So if you invert this and add a lambda, this means that we just renormalize this correlation length here with our parameter. And this is in some sense nothing else than the mass renormalization, which you know from quantum electrodynamics. So this is the mass of our propagator. In order to make contact with the one particle Green's function, we plugged in this corrected, lambda corrected susceptibility into a kind of equation of motion. So this is a rewritten equation of motion where we can put in directly the susceptibility. And in this way, these consistency relations become on the right and left hand side lambda dependent, and we have now two values of lambda. So we have a lambda density, so a lambda in the charge channel, we have a lambda in the magnetic channel, a lambda magnetic, and we have two equations, so we can solve for these two lambda parameters to renormalize our physical susceptibilities. And a simpler version of this was already introduced in the dynamical vertex approximation. So this is one of these diagrammatic extensions of DMFT, where you can see here that already if you only introduce a lambda magnetic and set the lambda density to 0, this helps a lot to improve the results. So the pink one is the self-energy now from d gamma A without such a correction. And you see that it has a wrong asymptotics, not the correct one of DMFT, while after a lambda correction, so this is the red curve here, you see that the asymptotics is on top of the correct DMFT asymptotics. So we now, what we have done is now we consider now both lambda corrections, both in the density and the magnetic channel. So let me start to present you the results we got from this. So first of all, let me consider only the Pauli principal equation. So where we consider the up susceptibility, so the sum of density and magnetic, where on the right-hand side, there is just this constant density. And if we have only one equation for two parameters, we can of course not solve it, but what we can make is we can calculate the lambda magnetic for different values of lambda density, and this is shown in this plot here, in this figure here. What you get is a monotonous behavior of this curve, which of course follows directly from this consistency relation. If you make the lambda density larger, you suppress the high density, so it becomes smaller, but you still have a constant on the right-hand side. So at the same time, you must make the magnetic susceptibility larger, which corresponds to a lower lambda correction in the magnetic channel. This somehow also mimics the mutual renormalization effects between the channels, which you have in a far more complicated way in Paquet. So you can really see how the charge and the spin channel renormalize each other in some way. They cannot be renormalized independently. Of course, the question is now how to fix this value of lambda density. Here we have many lambda densities, so we want to select one, and to this end we go to our second consistency relation, which is this consistency for the potential energy, and we look here now at the difference of the left-hand side and the right-hand side of this equation, again as a function of this lambda density parameter, and a 0 corresponds of course to a solution of this equation. And what we find is that at weak and also intermediate coupling, we indeed find such a solution, one single solution to this problem, while unfortunately at strong coupling, so far we couldn't stabilize the solutions, and the problem is obvious. If the charge fluctuations become too small, the inverse of the charge susceptibility becomes very, very large, and correcting this is of course numerically very unstable. Let us briefly look at the susceptibility. So first in the charge channel, in orange you can see the DMFT one, so the one without the lambda correction, and this is a local susceptibility, so just summed over k. So you can see that with our new approach we suppress this now because we have a lambda correction in this charge channel. And the same is true for the spin channel. However, for the spin channel, we can also compare to the old version of the ladder D gamma A, where we had only a correction of the magnetic susceptibility. And you can see that our new susceptibility in red, so when we include charge fluctuations, is a bit higher. And this is clear since part of the renormalization goes now to the charge channel. So the spin channel has not been corrected so drastically. Let us look at a special at the spin susceptibility evaluated as a special momentum and frequency, namely at the antiferromagnetic one. So at two values of the interaction, so one at weak and one at intermediate coupling. So first of all, we see that if we look at the inverse of this antiferromagnetic susceptibility as a function of temperature, we see a clear deviation from the mean field behavior for both the old, what I call now always old D gamma A version in green and the new one in red. However, what we also see is that, okay, both D gamma A versions give a lower T nail than the DMFT one, which is reasonable. So mean field theories overestimate transition temperatures. But what we can also see is that if we consider also the charge renormalization again, because we do not have to renormalize the spin so strongly, because partly we have the renormalization now in the charge channel, we get back a higher value of the nail temperature. So the crossing of the inverse susceptibility with zero happens at higher T nail. And this leads us to the phase diagram, where we can see that in the weak to intermediate coupling regime, we get an enhancement of our old D gamma A data in green to our new one in red, which is also more close to dual Feynman results or diagrammatic Monte Carlo results, of course not perfectly. On the other hand, in the strong coupling regimes, where charge fluctuations are frozen out already, we see no difference to the old version of the D gamma A, where only the spin has been corrected. So let me finally come to the energies. So first of all, the potential energy, this is actually the target quantity which we use for determining our renormalization parameters. So here you see here you see four curves. So again the orange one is the DMFT one, green and blue are the old D gamma A. There we have two curves, of course, because we are not consistent. In the old D gamma A, the left and the right hand side give different results. And what we observe as an effect of introducing a renormalization in the density channel is that we reduce the density susceptibility, and this at the same time, due to the first condition, the Pauli principle enhances the magnetic susceptibility, we get a rather drastic suppression of the potential energy. So we really find a solution with a much lower potential energy in this parameter regime. So we see this overall reduction of the potential energy with respect to the old D gamma A. And again, unfortunately, at really large values of U, where we could, on general grounds, expect another hierarchy of potential energies, we couldn't so far stabilize our equation. And finally, the kinetic energy. So let's start again with the weak coupling regime. So you can see that the old D gamma A, which is in green, was reduced with respect to the DMFT, which is actually not the correct physics at weak coupling, not this later physics. We would expect that the kinetic energy is enhanced there, and that's indeed what we find in our new version of the ladder D gamma A with the charge correction, while at stronger coupling, where again the charge fluctuations are small, there is almost no difference between these two approaches. Okay, so I think I will skip this slide. So this was the slide how we could also then in the next step introduce kind of conservation laws, but I guess I have no time for this. And so let me come to the summary. So we have discussed or have heard in this talk about diagrammatic, about thermodynamic inconsistencies in the dynamical mean field theory and its diagrammatic extensions. I have shown you a possibility to overcome them partly by introducing renormalizations, effective renormalizations of spin and charge fluctuations, which somehow mimics the mutual renormalization between the spin and charge, which is present in more complicated and complete theories like Paquet. And this leads to improved results for the nail temperature at weak to intermediate coupling in the Hubbard model. And with this, let me thank my PhD student, Julian Stobbe, who implemented all this formalism, and of course, you for your attention.